In this video, we're going to be discussing sampling distributions. In other words, the distribution first of the sample mean and then of the sample proportion in the next section. So let's read through the approach first in the first few paragraphs. Back in chapters 6 and 7, we learned about random variables and their probability distributions. In this chapter, we continue our discussion of probability distribution where statistics, such as the sample mean, will be the variable. So let me back up a second. In the past, we've talked about your height being the variable, or how much money you make as the variable. Now the variable will actually be mean, which is usually the thing we're looking for, but this time we're going to use the mean as our variable. Let me continue. For example, let's suppose that the government wanted to determine the mean income of all U.S. households. One approach is to take a census, which obviously is expensive and time-consuming. Another would be to take a survey of U.S. households and use the results to estimate the mean household income. This is already done as the American Community Survey, which administered to 250,000 randomly selected households each month. Different samples will lead to different sample means. For this reason, the sample mean x bar is a random variable, so it in itself has a probability distribution. The sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from a sample size of n. The sampling distribution of the sample mean x bar is the probability distribution of all possible values of the random variable x bar computed from a sample size of n from a population that has a mean and standard deviation. So for example, suppose that a simple random sample of size n is drawn from a population, and that population has a mean and a standard deviation. The sampling distribution, x bar, has a mean that gets closest and closer and closer and closer to the population mean, and a standard deviation that gets closer to the actual standard deviation. However, there will be over the square root of n, so it will change over time. And the standard deviation of the sampling distribution is called the standard error of mean. So obviously every time as far out as the standard deviation is going to go, that's called the standard error of the mean. How far is this x bar getting away from the actual population mean? The difference between those two is the standard error. Let's demonstrate this in an example. A survey was taken of 100 households in Valparaiso and found that the sample mean household income was x bar equals $44,650. So to recap, I went out and I randomly selected from Valpo 100 houses and asked them what their income was per household. On average, out of the 100 households, the average was $44,650. So I'm going to assume that this is a good indicator of what the population mean household income mu is going to be. Or is it? Well, it could be, but let's take a few more samples of 100 households each and then we'll compare. Okay, so again, I went back out into Valparaiso and I randomly selected another 100 households in Valparaiso, and I found that their mean income was actually $52,820. So you'll notice that these x bars aren't the same because I surveyed a different 100 people and I got a different household income. I went out and grabbed another 100 households from Valparaiso and got a different sample mean. This 100 got even a different sample mean. Okay, so you're going to notice that these sample means are in fact all different. So which one is going to be the best indicator of what the whole town of Valparaiso's average income is going to be? Well, let's Google the actual population mean income in Valparaiso. As of last year, in 2019, I found that the average income in Valparaiso at that time was $49,429. Okay? Now, what if we went back and we averaged all of these data? We took all of these and we averaged them all. In other words, added them all up and divided by 4. You're going to get an average of your averages of $48,547.50. Okay? So you can see that we weren't too far off from the actual population mean. But by averaging our means, we got a number that was closer to the population average. Okay, because none of these numbers were actually pretty close, except for maybe sample 3. But the rest of them, taking the average of them all, is the best way to get closer and closer to that population mean. So what the definition above actually states is that the sampling distribution of X bar has a distribution in itself. It has a mean, so you're taking the average of the sample averages, so it has an average of $48,547 with a standard deviation of, now I use StatCrunch to get this answer. Okay, I use StatCrunch to get this answer. Basically what this comes out to be is 3453 divided by square root of 4. So again, what I did is I put this information, these 4 numbers, into StatCrunch. I found the standard deviation of those 4 numbers, which comes out to be 3453. Then I divided by square root of n, which is, there were 4 samples, so square root of n. Then I found that the standard deviation of my sample mean was $1,726.50. Okay, so again, I used StatCrunch to find this answer. Two assumptions must be satisfied when sampling from a population. First of all, the sample must be a random sample. It has to be random. It can't be biased or convenience sampling. It has to be random. Also, the sampled values must be independent. In this case, we check to make sure that the sample is less than 5% of the total in the population. So in other words, again, the sample must be less than 5%. In this case, it is. 100 people, 100 households, is certainly less than 5% of all households in Valpo. Generally speaking, we don't really need to check this unless our sample size was really, really, really large. In one instance, sample sizes that are large is a good thing because you're getting a good estimate, but at the same time, you want to make sure that it's independent and that you're trying to make sure that these samples are not overlapping too much. Is it possible that somebody in this last sample was actually in the first sample? Sure, since it's random, it's possible that you'll select the same person for multiple samples, and that's okay, but we're trying to avoid a lot of overlapping. So we want to make sure that the samples are small enough that they're less than 5% of the population to avoid a lot of overlapping. So now let's move on to the central limit theorem. If the distribution of the population is unknown, let's say we don't know that it's normal, okay, so we don't know if it's skewed, normal, maybe no pattern at all. Let's just say we don't know, or maybe you know for sure that it's not normal, okay? Then the distribution of the sample mean becomes approximately normal eventually, provided that the sample size is greater than or equal to 30. So we're trying to get our sample size to be at least 30 if the original population distribution is not known or not normal. Okay. Now, if the population was normal, then we don't really care about this requirement, because every sample, if you're looking at a Venn diagram, if this is my population, and let's say that it is normal, then if I take a sample outside, then it is also going to be normal because it's inside of the normal population. So only we're caring about if the population is unknown, that's when we care about the sample size. We have to make sure it's large enough So that way we can assume that the distribution then is normal. So when you're asked to describe a distribution, we should talk about three things: the shape, the center, and the spread. Okay? Shape, center, and spread. So the shape of your distribution, we're looking to see that it's normal. So shape tells me what it looks like as far as is it normal or not. So if the population is normal, then regardless of the sample size, the shape of the sample is also normal. But if the population is not normal, in other words, it doesn't look like the symmetrical curve, then the sample size has to be at least 30. So in other words, as n increases more and more and more, the graph of the sample mean starts to look more and more like this normal curve up here. We generally say 30 is the minimum required. Now, where is the center of this graph? The center is going to be at the population mean. In this case, we're going to assume the population mean can be approximated by taking the mean of all of your sample means. So back from the previous page, when I add up all of my samples, all 4 of my samples, and I found the mean of all of my samples, it gets closer and closer and closer to the real mean. Now, what is the spread? In other words, how widespread is my data? Well, that's when I talk about standard deviation. So from the previous page, make sure your standard deviation of a sample mean is going to be the typical standard deviation that we would find using StatCrunch, but we have to divide that by the square root of n. So the larger the n, the larger the sample, the smaller that this number becomes because we're dividing by a really big number. So that means that the actual standard deviation is becoming smaller and smaller. So let's do an example of the gestation period. It says the length of a human pregnancy is approximately normally distributed with a mean of 266 and a standard deviation of 16 days. So right away I know that the population is normal. So I'm going to go ahead and draw a graph over here to the side just because I like to look at pictures when I'm doing problems. So if I draw the normal distribution curve, I know also that the population mean is 266 days for the normal human pregnancy. Now part A says, what is the probability that a randomly selected pregnancy lasts less than 260 days? This is the same thing that we've been doing back from chapter 7. So we already know how to do this. We're trying to find the probability that A means one person, one randomly selected pregnancy lasts less than 260 days. So in my graph, I could see, well, 260 is somewhere over here to the left of 266. And I'm looking for the probability over here of the pregnancy lasting less than that. So I'm looking for this probability in blue. So in notation, I'm looking for the probability that x is less than 260. Well, the first thing we need to do is we need to find the z-score. What z-score is 260 when I put it into the z formula do I get? Well, you're going to have to do the z formula down here. So z equals your data minus your mean divided by your standard deviation. So I get a z-score of negative 0.38. So that's what I'm going to use. So the probability that x is less than 260 is equal to the probability that z is less than negative 0.38. Then what I do is I go to the table. I go to table 5 and I look up the probability in table 5. Well, I've got table 5 in front of me. Hopefully you've printed them out as well. And I'm looking for a z-score of negative 0.38. So negative 0.38 is over here. So 0.3520. So the probability is 0.3520. So this probability right in here is 35%. So in other words, the probability that I'll select randomly a pregnancy that lasts less than 260 days is going to be 35%. Now, that we already know how to do that. That was back from the previous chapter. We're moving on now to how we can change that based on Chapter 8 initiatives. And in the second question, this is how it's going to change. So now we're going to randomly go into this bucket of names that have a bunch of pregnant women's names on it, and we're going to randomly select not one person, we're going to select 20 different women. And I'm going to select this random sample of 20 pregnancies. First, let's describe this distribution of these 20 pregnancies. When you're asked to describe, there are three things you need to use to describe. We have to describe the shape, the center, and the spread. Okay? The shape of this, we have to make sure that the population is normal. We'll back up in the question. It says that the length of the human pregnancy is approximately normally distributed. So when the population is normal, that means that the sample is also going to be normal. The center is going to be located at the average of all of your sample means. In this case, it's going to get closer and closer and closer to the actual mean, which is 266 days. The spread is the standard deviation of your sample means. In this case, it's going to be the standard deviation of your population divided by the square root of how many are in your sample. So the population standard deviation was given to us, which was 16 days, divided by the square root of n. In this case, n is 20. So when I put this into my calculator, I get a standard deviation of 0.0465. So this is how I would describe a sampling distribution. Talk about the shape, is it normal? Talk about where the middle of the graph is and how widespread the graph is, and that determines exactly what the graph would look like. So I'm going to use this information now to solve this next question. What is the probability that a random sample of these 20 pregnancies has a mean of 260 days or less? Now the question for you is, do you suspect that this is going to be a number that is less, greater, or about equal to the original, right? This is the probability that one woman will have this short pregnancy of only 260 days or less. I want down here the probability that 20 women will have this short pregnancy, or the average of their pregnancies will be this small. So do you think that the probability is going to change from the original? And if so, do you think it's going to be less likely or more likely? I'm going to do the problem to find out. Let's see if you were right with your prediction. So here I'm looking for the probability that the average of all 20 pregnancies is less than 260. So see already how that has changed. Here was just one person. Here is the average of 20 people. So first thing we do, just like we did up here, we turn that into a z-score. In order to find the z-score, I have to put it into the z formula. So the z formula says I take the data, which is 260, minus the mean, which is 266, divided by standard deviation. I don't use the original standard deviation. I use the new standard deviation, which is much smaller. Sorry, I just realized there was an error up here. This was supposed to be 3.57. My apologies for that. If you were already looking at that and putting that in your calculator and you're like, oh, well, how did she get that answer? It's because it was wrong. I'm sorry. So that was the standard deviation. So the standard deviation I'm going to use down here in the z formula is 3.57. All right, so now I put this into my calculator. I'm actually going to do it this time and not just put down the answer that I had written, because last time it was wrong. So I put this into my calculator and I get a z. It looks like it is negative 1.68. So this is the same probability. This time my z has changed from the original z. Okay, this z is farther away from the mean than this z up here. So I go to my table 5. So now I go to my table 5 and I find the probability that a z is going to be less than 1.68 negative. So here in my table I've got a z-score of negative 1.68 and I find the probability is 0.0465. So my probability is 0.0465. So you can see how this probability did indeed change. It got much smaller or much more unlikely, right? So think about that again. If you go into a room and you randomly say, okay, you know what, I want to select one person with blue eyes. It's fairly likely, right? There's probably a good percent of the people in the room that have blue eyes. So it's fairly likely that you'll select somebody with blue eyes. Now you go back into the room and you say, okay, now I'm going to select 20 people that all have blue eyes. What's going to happen to your probability? It's going to get less and less likely because you're selecting multiple people that all have that characteristic or all have an average of that characteristic, right? So it's going to become less and less likely. So the larger that your n is, the less likely it becomes to obtain that particular characteristic. So what do you think is going to happen in question D when it asks for the probability that a random sample of 50 pregnancies all have a gestational period of 260 days or less? Well, it's going to become even less likely. So this probability is going to get even smaller. So I'd like you to pause the video and try that one on your own. Here's what I got. Did you make sure you changed your standard deviation? Over here, when we're figuring out what our new z needs to be, make sure you're changing your standard deviation. It's your raw data minus your mean divided by standard deviation. This time our standard deviation is going to be 16 divided by square root of 50 because I have a larger sample. So our standard deviation changed. It is no longer 3.57 and it is no longer 16. It's going to be this number, which is much, much, much smaller. So when I calculate this, my z-score becomes negative 2.68. And when I look that up in table 5, I get a probability of 0.0040. So the last question says, what do you notice about the relationship between C and D? In other words, as the n is getting bigger, our probability is getting smaller. So as n increases, the probability gets smaller. And the reason why that happens is because as n gets bigger, your standard deviation is getting smaller. And that's what's causing the probability to change. Okay, so let's do an activity that will probably bring this all together for us. Here's an activity. If we were in class, I would ask you to get into groups, so we're just going to picture what would happen here. And I've got the following data that represents the running length time in minutes of the winners of the Oscars for Best Picture for these 6 years. Here's the winners for Best Picture for these 6 years. And here's how long each of those movies were. Okay? The first thing it says to do is compute the population mean. The population, if this is the population, there's 6 movies in my total population. Okay? This is my total population right here. And it says compute the population mean. So to find that, I simply just add all of these up and divide by 6, right? So my population mean is going to be the sum of all of the minutes divided by 6. So the sum of all of those minutes is 768 divided by 6, and I find an average of 128 minutes. All right, so we already know what the population mean is, but we're going to go through an exercise and pretend we don't know what that is, right? Generally, the population is much bigger than 6 items. So what we're going to do is we're going to list all possible samples that have a size 2 in the left column. I know that there's going to be a combination of 2 out of 6 samples because we know how to do that back from chapter 5. A 6C2 is 15. So we know that there should be 15 total samples. To give you an idea, one could be $1 Million Baby and the movie Crash. That's one sample. So if I go into this bucket of 6 movies and they all their names are on a piece of paper and I randomly pick out 2, I could pick out this combination. I could pick out $1 Million Baby and the next one, which is The Departed. I could pick up $1 Million Baby and No Country for Old Men. So what I'd like you to do is pause this video and see if you could come up with all 15 samples. In other words, you're going to fill this total table in with all possible combinations of 2 movies each. So pause the video now and fill in this table. Okay, so I've already done that. I've listed all 15 combinations. Your order might be a little different than my order, and that's fine. But I've listed all 15 combinations. So if you didn't find them all, pause the video and fill in the rest of your table with the one that you're missing. Then for step 3, it says construct a sampling distribution for the mean by listing the sample means in the right-hand column. In other words, $1 Million Baby and the movie Crash, these first 2 items right here, have an average of 132 and 112, has an average of 122 minutes. That would be the sample average of those 2 movies. The sample average of $1 Million Baby and The Departed is going to be the average of 132 and 155. And that average is 141.5 minutes. So at this point, I'd like you also to pause the video and see if you can find the rest of your sample averages, and they're going to go in the same order that you have on your paper, which might not be the same order that I have. So go ahead and fill in the rest of your table. So pause the video now. Okay, so after you're done with that, then step 4 says to now let's compute the mean of the sampling distribution for the by finding the average of the averages. So what I'd like you to do is this last column right here, find the average of all of these averages, and theoretically that should get closer and closer and closer to the population average, which we already know is 128. So I'd like you to pause the video now, and I'd like you to find the average of these averages. You should have gotten the same thing. I added all of these up and I got 1,920 when I added up all of the averages. I divided by 15 combinations and I got the exact same answer. And that's the whole theory on why this works. I mean, it's only going to be exact. They're only going to match if you found every single sample from the whole population, which in theory isn't going to be possible for most populations. But for this example, since the population was so small, we were able to do that. It does work out. They end up being the same. It wouldn't have mattered if I selected samples of size 3 or 4 or 5. This was going to happen regardless. The average of your averages is always going to be equal to the original population. So that's what I noticed about number 1 and 4 is they're the same. So now what it says for step 5, it says compute the probability that the sample mean is within 5 minutes of the population running time. Okay, so what it's asking me to do is find the population mean. So let's see, I started the problem here for you. I'm going to cover up the answer. Okay. So here we're supposed to compute the probability that the sample mean is within 5 minutes of the population mean. So here's the population mean, which we know is 128 minutes. And we want to compute the probability that the sample is within 5 minutes. So 5 minutes to the left or 5 minutes to the right. And we got to find the probability of the shaded area in between 123 to 133 minutes. So what's the probability that that average is going to be in between those two times, right? So the first thing I do is, again, I turn those numbers into z-scores, and that's what I did here. Okay, the z-scores are going to be for the left number, 123 minus 128, divided by the standard deviation. Now the standard deviation for the population is 13.49. I found that from StatCrunch. I make sure I divide it by square root of 2 because there's 2 movies in my sample. And I do the same thing for the z-score for 133. And I find that both of these z-scores are going to be between negative 0.52 and positive 0.52. Of course, they're the same number, just opposite signs, because they are equidistant from the mean. They're the same distance from the mean on both sides, so they're going to have the same z-score, just one's going to be negative, one's going to be positive. So to find this answer, I go to my table 5 and I look up both z-scores and I find the probability of both of them and I subtract those two numbers. So I find that the probability then is going to be 0.6985 minus 0.3015, which gives me a probability of 0.397. Make sure you always put the bigger z-score probability in first because that's going to be the bigger probability. You don't want to subtract the other way around. You'll get a negative probability, which we know can't exist. So let's say for this last example, you finished before all of the others in the class. I'd like you to discuss in your group how the situation would change with sample sizes of size 3 instead. So let's go ahead and talk about that. What effect would this have, right? Okay, so here we've got more samples. If I want to select 3 out of the 6 movies, I'm going to end up with more samples. Instead of just 15 samples, I'm going to have 20 samples of 3 movies each, right? So I'm still looking for the same shaded area over here, but my samples are going to be bigger. My N is bigger. Because N is bigger, we know from the previous page that this is going to make my standard deviation smaller because you're dividing by a bigger number, making the standard deviation a bigger number, meaning the z-scores are going to be smaller. So this graph is going to be more concentrated in towards the middle, which makes the data values move farther away and a larger inside area. So for example, if I just did an example for you here, the z-scores you'd be dividing by square root of 3 instead down here, which makes your z-scores, they're going to be larger numbers, right? Because you're dividing by this smaller standard deviation. So because these z-scores are going to be bigger numbers, you're going to have a larger area in between because these two values seem to be moving farther and farther away from the mean because you're ending up with a different standard deviation. So therefore I'm going to get a probability of 0.478. So the probability did in fact go up.